Welcome to the Excitable Cells as Dynamical Systems module part 3, Excitability and Bursting. In the previous lecture, we discussed bifurcations of the resting state and of the tonic spiking in a simplified model of a neuron. In this lecture, we'll look at the implications of a neuron undergoing bifurcations of a certain type on its physiological and neurocomputational properties. We shall call a neuron, or a model, or a system, excitable if a small perturbation from a resting state evokes a stereotypical response which makes large excursions in the phase plane, namely in voltage mostly, and called an action potential or a spike, and then returns back to the resting state. So this would be an excitable system. If at a given set of parameters, the model or a real neuron exhibits regularly spaced spikes generated intrinsically, we shall denominate this behavior periodic spiking, like here. Or we can call it a limit cycle or tonic spiking. Indeed, the stable resting state and tonic spiking regimes can coexist at the same parameter values in some systems, and short, correctly timed perturbations can switch the neuron from quiescent to firing modes. Such systems are called bistable. In other cases, a system can spontaneously flip from spiking to quiescent states, so it flicks between spiking and quiescence. And the groups of spikes are called bursts, and they are separated by larger gaps. Such a regime is called bursting, and it can be periodic or stochastic, and further down the lecture we'll see what role can it serve in computational properties. It was Hodgkin who first did a kind of bifurcation analysis of a neuron excitability. He studied giant axons of the squid and found that different axons respond to long depolarizing steps in different ways. So some neurons dubbed as class 1 were class 1 excitable. They started generated low frequency spiking at relatively low amplitude current steps, and the spike in frequency increased gradually with the stimulus amplitude. So the increase in stimulus current led to increase in spike in frequency over a broad range of frequencies. On the other hand, class 2 neurons didn't have this broad frequency range. They didn't encode the intensity of input current as a frequency code. So when the stimulation current was low, they didn't sustain periodic spiking and only showed transient responses or phasic spiking. At higher stimulation amplitudes, however, they did sustain periodic spiking. Now let's look in more detail at the first two cases, at these two cases, using our simplified persistent sodium plus potassium current model. The type of response is dictated by the type of a bifurcation from the resting state, and our model can display all four bifurcations that can there be, and thus both class 1 and 2 class 2 and class 2 responses. So when the system is near the saddle node on invariant circle bifurcation, it displays a typical class 1 excitability, shown here. At low stimulus amplitudes, it produced low frequency spikes. At high stimulus amplitudes, the spiking rate gets much higher. Well, all three other bifurcations, namely saddle node off invariant circle and the two Andronov-Hopf bifurcations, lead to class 2 excitability, exemplified here by a supercritical Andronov-Hopf bifurcation of the spiking state. A sudden jump in the frequency at large applied currents is quite obvious. And in the next slide we'll illustrate how they differ in their neurocomputational properties, but we can see now that the neuron of class 1 excitability, or saddle node invariant circle, actually do encode the applied current in spike in frequency, while the neuron at supercritical and Andronov-Hopf bifurcation have a much lower frequency range, and it starts to respond with tonic spiking only at very high applied currents. So just to remind, there can be 4 types of bifurcations from resting state, namely 2 saddle node bifurcations and 2 supercritical Andronov-Hopf bifurcations. In the saddle node bifurcations, we have 2 equilibrium points, a stable node and a saddle, and as our applied current shifts the V0 line upwards, these 2 equilibrium points merge together and annihilate each other. So these are saddle node bifurcations. In the Andronov-Hopf bifurcations, on the other case, we don't see a change in the number of equilibrium points, but before bifurcation we have a stable focus, and just after the bifurcation the focus becomes unstable. Now, because there is a focus in the Andronov-Hopf bifurcation, this means that the dynamics of the neuron is oscillatory near the resting state. So the return to the resting state is oscillatory, whereas the return to the resting state in the saddle node bifurcations is monotonic. And it doesn't matter whether we hyperpolarize or depolarize the neuron, the return would be monotonic. And in the Andronov-Hopf bifurcations, the response to a depolarizing stimulus and the response to a hyperpolarizing stimulus both will be non-monotonic or oscillatory. For example, if we have a hyperpolarizing stimulus, we first hyperpolarize the neuron, but then it returns to the resting state with damped oscillations. We can see it in some more detail in here. So the neurons with saddle node bifurcations can be called integrators, because what they basically do, they integrate the incoming depolarizing stimuli. So each depolarizing postsynaptic potential or postsynaptic current will try to move the system towards the separatrice of the saddle, which is the threshold in these kind of neurons. And each inhibitory stimulus or inhibitory postsynaptic current will drive the system away from the threshold. So in a way, the saddle node neurons integrate the input. A different case is seen in Andronov-Hopf neurons. So such neurons which can be modeled by a dynamical system that is near the Andronov-Hopf bifurcation. And here the threshold manifold is actually curved, so the system can produce a spike starting either from here or from here. So the neuron actually don't have to be strictly depolarized to make a spike. You can hyperpolarize a neuron and still get a spike. This means that it's not the direction of the postsynaptic current that matters here, but the timing, because if the timing is correct, you move the system towards the threshold, but if the timing is incorrect and it comes at the wrong phase of the cycle, then you actually move your system or neuron closer to the resting state. On the other hand, inhibitory pulses or hyperpolarizing pulses can also lead to a spike if they're applied in a correct phase of the intrinsic oscillation or intrinsic subthreshold oscillation. Now let's look how the model neurons respond to short current pulses. So our stimulation protocol is shown in the lower parts of the graph, and we demonstrate this behavior for the integrator and the resonator. So if we look at the integrator, then we can see that so we test the system with a subthreshold pulse. So a response to one pulse, one depolarizing pulse, is monotonic. A response to one hyperpolarizing pulse is also monotonic. And then if we provide pulses within integration window, we gradually get response, and the higher the frequency of the incoming pulses, the smaller is the delay between the onset of the stimulus batch and the response that we have, the action potential. Now, if the bursts of stimulation pulses are outside the integration window of the current neuron, then we don't see spikes. Now, response to inhibitory and then immediately after depolarizing stimuli doesn't lead to a spike either. The same dynamics can be seen in the movie, and which I'll show presently. So this is the movie, and what we see is, now we'll get very soon here, then we see a single depolarizing pulse. Now this time we'll get a batch of pulses and a spike. So yes, here we go. We actually allowed the neuron to spike. Now the next batch is still within the integration window, although with a larger spacing between the pulses, but still we can obtain a pulse. Now the next batch will be outside the integration window, and we see that the neuron returns back to the resting state just after each stimulation pulse. Now there is no interesting behavior of the system anymore. Now let's see how a resonator, or neuron near subcritical Andronov-Hopf bifurcation, behaves within the same stimulation protocol. We can see that the response to a single subthreshold pulse is actually oscillatory. Now, short-spaced batches of stimulation pulses don't lead to action potential because they're outside the resonance window of this neuron. Now, the resonant burst of the stimulation pulses does lead to action potentials or spikes because they're applied in the correct phase. We can also see another thing, which is called a post-inhibitory facilitation, where this response, a non-monotonic response from an inhibitory pulse, actually drives the system towards the threshold and facilitates generation of a next spike. This can be also shown in a video demonstration like here. So at time 50 and just after 120, you'll see that, okay, this was a response to a subthreshold pulse. Then would be a response to a couple of non-resonant batches. You can see that the applied current changed too fast for the neuron to actually respond to it. So they're out of phase, out of sync, if you wish. So high frequency batches don't help the neuron to fire. Real neurons are bombarded by postsynaptic currents at tens of thousands of synaptic connections at various timing and having either depolarizing or hyperpolarizing effect. Let's then look how the simplified model near the 4 types of bifurcations behave if driven with noisy input. So this is the neuron near saddle node and invariant circle. This is saddle node off limit cycle. This is suprathreshold, and this is a subthreshold Andronov-Hopf bifurcations. And I use the same pseudo-random applied current and see how the neurons near the different bifurcations respond to this noisy input. can be readily seen that both systems that are bistable, so this one, oops, I'm sorry, these two, the bistable neurons, tend to fire spikes in batches. So they tend to produce bursts of spikes. And both resonating neurons have rich subthreshold oscillations. For example, the supercritical Andronov-Hopf bifurcation will produce a number of weird small amplitude spikes in activity, which, not all of which, will be able to initiate downstream action potentials propagating through its axon. Now, in contrast, the neuron near saddle node on invariant circle bifurcation will show a classical Poisson process-like spike trains. So this would be very, very canonical for computational neuroscience, because computational neuroscientists kind of like to simulate a neuron with a Poisson process. I'll put it in quotation marks because it's not more canonical than any other of the bifurcations. Now, to summarize, integrators or integrated neurons lose stability through saddle node bifurcations. Some can feature spiking with arbitrary low frequency, and they have a well-defined threshold and always distinguish between excitatory and inhibitory stimuli in a predictable way. And they integrate over their incoming currents, and the higher the APSP frequency or excitatory postsynaptic current frequency, the sooner they'll fire. On the other hand, resonating neurons make the resting spike and transition via Andronov-Hopf bifurcations. They may not have all or none spikes because they can have partial amplitude spikes, and prefer to fire spikes within a specific frequency band. These neurons exhibit subthreshold oscillations, and inhibitory pulses can lead to spiking if applied at this precisely matching time points. So input frequency outside the resonance band will be less effective to drive spike generation, even if it's high frequency stimuli. Now, what happens if we slowly modulate the applied current? So our applied current will go up and down, and thus we will drive the system first through the bifurcations from the resting state, and then through the bifurcation of the spiking state. Now, for example, here is a neuron near saddle node off invariant circle bifurcation, and it undergoes a transition from resting to spiking via SN off. And you can see that after a delay there is immediately high frequency spiking, but it goes back from spiking to resting via the saddle node on homoclinic orbit bifurcation, and that's why it has slowing down of the spiking rate or increasing interspike intervals. If you remember, that's because of this slow corner near the saddle. So that would be a saddle. Actually, yeah, that would be a saddle. And I was almost drawing a note here. But anyway, so that would be a saddle, and near it there is a limit cycle. And as it passes near this slow corner, so the spiking rate decreases. Now, in the case of, for example, supercritical Andronov-Hopf bifurcation, what we observe, we don't observe any change in frequency, but we do observe after latency a slowly increasing in amplitude spikes, and then when we wane from spiking state, we do this again via supercritical Andronov-Hopf bifurcation, and thus we see the gradual decrease in the amplitude of spikes. Now, this latency is to the first spike is explained by the low real value of the eigenvalues, or low amplitude of the real values of the real parts of the eigenvalues. So the dynamics is slow. Now, this leads us to natural bursting, or neurons that tend to fire in batches of spikes, or bursts of spikes. So previously we just saw a forced bursting when we modulated the applied current, but then there is of course an intrinsic bursting, and quite often we can separate the system into two, the neuron into two subsystems: a fast or spiking subsystem that explains the actual action potentials, and a slow subsystem which modulates or drives this fast subsystem through bifurcations. For example, in a slow wave bursting, a slow subsystem is completely insensitive to the fast subsystem, and the slow subsystem dwells in some oscillatory regime, and thus it has to be at least two-dimensional. So the slow subsystem just undergoes oscillations, and then the fast subsystem produces spikes because it's driven through its corresponding bifurcations. Or if there is a bistability of resting and spiking states in the fast subsystem, like in the saddle node off invariant circle or subcritical under and off bifurcation, then the slow subsystem can form a hysteresis loop and lead to transitions between spiking and non-spiking. So there can be 16 types of bursters or bursting neurons, which is predicted from the structure of the model, because a neuron can lose its stability through 4 kinds of bifurcations, and it can lose spiking state through 4 different types of bifurcations of the spiking state. Now, the reason that bursting behavior is widely employed by the nervous system is not completely understood, but it tends to researchers tend to think that sometimes a burst of spike can be more efficient in releasing transmitter from synaptic connections from the presynaptic part of the synaptic connection, or with bursts at different frequencies, a neuron can activate different kinds of resonator neurons, because different kinds of resonator neurons can have different intrinsic frequencies and be sensitive to differently spaced spikes within the burst. So this actually widens our possibilities of coding the information within the neural networks. So one way to code information is through rate coding, such as the intensity of the stimulus is encoded in the frequency of spiking. And another coding is timing coding, so that the information is conveyed by the phase or the difference of onsets of spikes. And probably bursting has an important role in this kind of coding. For the further reading, again, there's a book by Zhukevich and a couple of papers, and my acknowledgements for professional assistance and encouragement from Olga Sosnovtseva from the Department of Biomedical Sciences, University of Copenhagen, Denmark. Thank you very much.